All right, let's get right into it. The world around us is buzzing with invisible forces, pushing and pulling on everything. But what if you could actually see them? What if you had a tool that let you not just see these forces, but use them to predict how anything is going to move? Well, believe it or not, that's exactly what we're about to do.
You ever wonder about stuff like this? I mean, a book on a table just sits there, doesn't move an inch. But a skydiver, they have this whole journey, right? They speed up like crazy, and then suddenly they're just falling at a steady pace. They seem like complete opposites, but the answer to why both of these things happen is exactly the same. It all comes down to an invisible battle of forces.
So how in the world do we make these invisible forces, well, visible? The secret is a tool that is so simple, it's brilliant. It's something scientists and engineers use every single day, and it's called a force diagram. This is our key to solving the whole mystery. And that's really all it is. Seriously, a force diagram is just a simple sketch. You draw the object, usually just as a box or a dot, and then you draw arrows pointing away from it. Every arrow stands for a different force, and when you put them all together, they tell you a story.
Now, reading this story couldn't be easier. There are only two rules you need to remember. First, wherever the arrow is pointing, that's the direction the force is going. Simple. Up, down, left, right. Second, the length of the arrow tells you how strong that force is. So a really long arrow means a powerful force. A tiny little arrow, a weak force. That's it. Direction and size.
Okay, so we know how to read the arrows. Now we get to the most important part, the whole reason this works. With just those two rules, we can understand the crucial difference between what we call balanced and unbalanced forces. This is everything. So you've got two possibilities. On one side, you have balanced forces. This is when all the forces are equal and opposite. They basically cancel each other out. And the result? No change in the object's motion. On the other side, you've got unbalanced forces. This is when one force is stronger than another. They don't cancel out, and that leftover force is what causes a change in motion. It's what makes things speed up or slow down.
And the best way to think about this is a game of tug of war, right? If you have two teams pulling with the exact same amount of strength, what happens to that rope in the middle? Absolutely nothing. It just stays put. The forces are perfectly balanced. But the second one team pulls just a little bit harder, the rope starts to move. The forces are now unbalanced.
Let's bring this back to our book on the table. We can finally draw its force diagram. You've got gravity pulling the book down. That's one arrow. But at the same time, the table is pushing back up with a force that's equal and opposite. That's our second arrow. Because the forces are the same strength, the arrows are the same length. They're perfectly balanced. So our prediction? The book's motion won't change. It was still, so it's going to stay still.
So there we have it. That's the whole toolkit. We know how to draw the diagrams, we know how to read the arrows, and we get the all-important difference between balanced and unbalanced. So let's put it all together and start predicting how things are gonna move.
Okay, let's start with the easy one we already know. A box is just sitting there. The force of gravity pulling down is perfectly matched by the floor pushing up. The forces are balanced. So an object at rest stays at rest. Check.
Now, this is where it gets super interesting, so pay close attention. What if something is already moving, but it's moving at a perfectly steady speed, not speeding up, not slowing down? Well, if you're pushing a box across the floor at a constant speed, your forward push is being fought by the backward force of friction. If those two forces are equal, if the arrows are the same length, then the forces are, you got it, balanced. This is so important. Balanced forces just mean no change in motion. It can mean sitting still, or it can mean moving at a constant speed.
So, what do you have to do to make something actually speed up? Well, you need to create an unbalanced force. If you want that box to accelerate, your push has to be stronger than the force of friction pulling it back. And you can see it right there in the diagram. The arrow for the push is longer than the arrow for friction. The forces are unbalanced, and that difference is what causes the object to accelerate.
All right, it's time. We've got all the pieces of the puzzle. Let's go back to our skydiver and solve this mystery once and for all, mapping out their entire journey using what we now know about force diagrams.
This is just a beautiful example of how forces can change. Okay, stage one, right after the jump. Gravity is pulling down hard. That's a huge arrow pointing down. Air resistance is barely there, just a tiny arrow up. The forces are massively unbalanced, so the skydiver speeds up, fast. Stage two, as they fall faster, the air pushes back harder, so the air resistance arrow gets longer. But gravity is still winning. Its arrow is still longer. The forces are still unbalanced, so they keep accelerating, just not as much. And then finally, stage three, terminal velocity. They're going so fast that the upward force of air resistance has grown to perfectly match the downward force of gravity. The arrows are now the same length, the forces are balanced. And what happens when forces are balanced on a moving object? It stays at a constant speed. Mystery solved.
So here's the big takeaway. Force diagrams are kind of like a superpower for seeing how the world works. They take all these complicated physics ideas and turn them into a simple visual story. If you can figure out what forces are acting on something and draw them out, you can predict exactly what's going to happen next. It's one of the most fundamental tools in all of science for very good reason.
So now you have the tool. You know how it works. I'm going to leave you with a little challenge to try out your new skills. Picture an airplane just cruising along at a constant speed and a constant altitude. What forces are acting on it? What would its force diagram look like? If you can picture those arrows in your head, then you're already starting to think like a physicist.